All right. Well, hello, everyone, and welcome. My name is Laurel Glenn. You probably see me on a couple of these webinars. And I'm the project manager for safety at the Virginia Tech Transportation Institute. And I also have Aaron with me as well for this webinar today. So we appreciate you joining the webinar on the measuring of safety of automated driving systems. Just as a reminder, you have all come into this webinar muted and your cameras are disabled. If you have questions during the presentation, please use either the question and answer option, which is at the bottom of your Zoom screen, or the chat box, and we will get to those. You can also use that feature if you want to share any documents or just share something with the public at large in general, or the attendees at large. If you'd rather ask your question yourself, we highly encourage that. And we just ask that you raise your hand or just let me know via chat, and I will unmute your mic and video for you to do that. So you can discuss things with our presenter at the end during the question and answer session. We encourage that conversation as long as you're comfortable to do so. And also captions will be on for you at your convenience. So at this time, I would like to take the moment to introduce your presenter today, Eileen Erbers. She recently became a research associate at the Virginia Tech Transportation Institute. She received her BS in Applied Mathematics Engineering at Northwestern University in 2018 and is so close to receiving her PhD in Engineering Mechanics from Virginia Tech. That should be this semester. So this project formed a significant portion of her dissertation research, which focused on using naturalistic data to measure the potential safety impact of automated driving systems. She was also just named the Student of the Year for the Safety Through Disruption University Transportation Center and was honored in DC for that earlier this month. So without further ado, Eileen, take it away.
All right. Thank you, Laurel, for that intro. Let's see, and you all can see my presentation title screen here? Great.
Yes, we can.
Okay, perfect. So I've had the privilege to work on a lot of UTC safety projects. And like Laurel said, this one makes up a large portion of my dissertation. And so I will be talking about measuring the safety of ADS and how safe is safe enough. I understand this is kind of a hot question in the industry, and there are a lot of opinions on how to determine how safe is safe enough and what that means. But before that, I will go ahead and first describe what ADS are. So ADS are automated driving systems. So from the Society of Automotive Engineers, SAE, the J3016 standard describes the 6 levels of automation. And the easiest way to distinguish between levels is who is in charge of different aspects of driving. So steering and acceleration or deceleration, monitoring the driving environment, and then the fallback when automation fails. So when that dynamic driving task needs a fallback. And then where these vehicles can operate, so that operational design domain. So this project is looking at ADS and specifically levels 3 and 4 of automation. So these, essentially the vehicle is in charge of monitoring that driving environment. So levels 0 through 2 require the driver to be involved at all times, whereas the level 3 and 4 allows the vehicle to monitor the driving environment so the driver can take their eyes off the road. But the fallback when automation fails changes between level 3 and 4. So in level 3, the human is in charge of that fallback, and in level 4, the vehicle is involved in that fallback. Both of them have limited ODDs. So for this project, we're looking at ADS, essentially levels 3 and 4. The bigger part of this research is answering the question, how safe is safe enough? And like I said, it's a hot button topic. It does seem like a simple question. We just have to decide a threshold of safety that determines if ADS can be deployed or not. But there are a lot of questions that come up when we try to answer this one. Like, how do we define what is acceptably safe? Safety is a complex concept, and to simplify it, we can view it as the reduction of risk. And in that case, what risks do we currently accept on the road? When we get in our cars to drive to work and run errands and do everything we do, we inherently accept some risk. So the question is that risk right now acceptably safe? We'll kind of discuss that a little bit later. But then additionally, do ADS reduce any of the current risk on the road? And that's the hope, right? If we can remove crashes due to human error, then we can remove a lot of crashes from that environment. So ADS can reduce the current risk, like driver distraction and driver impairment. But a bigger question is, do ADS create any additional risk? This is especially where public opinion begins to become louder, because people are afraid of ADS and making sure that it isn't creating any additional risk. And there are a lot of unknown unknowns. So a common answer to this question is that as long as the ADS is safer than a human driver, then it is safer. This could be our threshold. But this answer brings up even more questions, like which human driver? We all know people that drive more safely than others. And then also under which conditions. So not just weather and lighting conditions, but road type of vehicle, other risk factors present while driving, a lot of the unknown unknowns, like I mentioned before. And not only that, but human drivers are not that safe to begin with. We've seen an unfortunate increase in traffic fatalities on US roadways over the years. And in 2022, estimates show that over 42,000 people died on US roadways. So if our threshold are these crash fatalities, if there are only 41,000 deaths after the introduction of ADS, does that mean that they're safe enough? What is that threshold that we'll allow or will accept? And then what is acceptable to the public? What is acceptable to policymakers? Which brings up even more questions about how to measure that acceptance criteria. So another question is, who defines what is acceptably safe? The vehicle and technology manufacturers, policymakers, safety professionals, the public, both people using ADS and then those sharing the road with ADS, all have different definitions of what is acceptably safe. And then how is ADS safety and performance, ADS performance tested? So there's simulation and closed test, track testing, and field testing. But then how are these testing scenarios selected? What do they test? And that also brings up the question, what metrics and thresholds are used to determine safety? How are those thresholds determined? How do we create kind of that cut line? It gets very complex. And then who is at fault if ADS are involved in a crash? Now, this one is more on the law side of things and who is required to ultimately back up a safety claim. I'm generally steering clear of who's at fault, but it is such a common question when this topic is brought up. So I would be remiss to not mention it at least. And there might be some people listening that also have this question. And this research focuses on using naturalistic data to determine safety metrics and performance. So we're not necessarily answering these specific questions, but instead delving into some data that could be used as a tool to measure ADS safety. So that brings us to the purpose of this research. And the part of the purpose is to use naturalistic driving data to inform scenario selection that will be used to measure how ADS might perform in those scenarios. So similar to that, we're determining and analyzing some scenarios in which ADS may not provide the predicted advantage of reducing or mitigating safety critical events. So the thought that ADS can reduce our risk, we have to make sure that we're looking at all of those scenarios specifically so that we can compare apples to apples, scenarios with human drivers to scenarios with ADS. And safety critical events are generally crashes and near crashes. So crashes that were avoided from a successful evasive maneuver, essentially. So looking into the methods, naturalistic driving data is where vehicles are equipped with cameras and data acquisition systems to measure driver information and vehicle kinematics of drivers during their normal driving habits. So the vehicles are instrumented with these devices to capture what happens during their normal commute and normal driving. So in this data, we identified 2 areas in which we believe ADS may have trouble performing based on a previous project. And so this was first looking at the operator factor, and these crashes and near crashes were the fault of the other driver. So that means the driver in the vehicle that was equipped with these systems were not determined at fault, and it was fault of the other driver. So ADS may have difficulty predicting erratic behavior of other users on the road. And that's kind of the point why we chose that one. And then where a visual obstruction was present. So ADS may not have enough time to predict a potential conflict and perform the correct evasive action due to sensors being blocked either by other vehicles on the road or foliage or a large hill. Lots of other, whenever there's a visual obstruction, essentially. And so for this selection of cases, we had 3,007 cases, events, crashes and near crashes, and we separated them by configuration category. So these configuration categories are based on the direction of the vehicles, of the subject vehicle, and then that conflict object at the time of the event. So there's the angle, sideswipe, merge, and cut in. So that's where they're going the same direction. The forward impact, these are generally rear end crashes where they're both going the same direction in the same lane. And then perpendicular crashes, pretty self-explanatory. Head on is where the vehicles are initially going the opposite direction, either in the same lane or in opposite lanes or in offset lanes. And then backing up was just a small number of events where it was mostly parking lots. People would back up into cars going through. And then roadside departure was also included. It was looking more, that was that kind of traction control loss, or if there were any evasive maneuvers that required the subject vehicle to go off the road. And so for the methods of this project, we identified 4 time points based on the radar data that was available. So using these time points and the vehicle kinematics, we calculated some other variables, but these times were T0, where the conflict object was identified by the radar. So that's just when that conflict object was first identified. And then the conflict begin, that's when the ADS would have predicted that a conflict would begin, or in the video, it looked as if a conflict were to occur. But then T2 is when that subject, the vehicle driver actually reacted. So they braked, or they swerved, or they noticed the conflict and acted in some way that we could see in the kinematics. And then T3 is that impact or proximity frame. So that's when there was actual contact in the crash, or the closest point of contact in near crashes. And so then we used these time points to calculate 3 safety surrogate measures, including the kinematics as well. And all these 3 are related but used differently. So the relative velocity is the difference in velocity between the subject vehicle and that conflict object. The time to collision, or TTC, is one of the most common safety surrogate measures. It measures the time that the host vehicle would collide with the conflict object based on the current distance and relative velocity. So this assumes that the host vehicle and the conflict object will continue on their current trajectories at the current velocities. So this is commonly used to measure the potential severity of collisions, even if there is not a collision, like a near crash. And then the minimum required deceleration is the smallest absolute deceleration value required to avoid the collision, as if the trajectories of the subject vehicle and conflict vehicle do not change at that point. So this value is actually already inherent in the TTC calculation, but the minimum required deceleration can be more easily compared to deceleration rates already set in ADAS or ADAS features, so L1 and L2 equipped vehicles, like automatic emergency braking. So the lower the value, the less braking that is required to avoid the crash. And then a large portion of this project included video review. So it was included to validate that these timestamps and the values calculated are reasonable, to make sure that the radar didn't cut out at any weird moments. And then it was used to identify outlying cases. So we'll kind of describe some of those later on, but these were important to look at and figure out why some of the values were outliers. And then it was used to categorize scenarios. So after reviewing a lot of video, we were able to establish maybe some scenarios that ADS would have trouble with maneuvering in the correct way. So here's some results from the time to collision, or TTC value. So here we compare the average TTC for when the subject reacted, which is, you can see in that orange pink color, versus when the average of when ADS would react to a potential conflict, which is in purple, for each configuration category. So this was the average TTC at time points T1 and T2, respectively. So we can see that on average, the ADS would allow for a larger TTC. So that purple box, the average is generally higher than the pink one. And so this shows that ADS would allow for a longer time to react before a potential collision. So on average, ADS provided an additional 2.23 additional seconds of TTC across all 7 categories. So that's averaged entirely. Like I said before, what is important to look at are these outliers. So for example, if we look at this one circled in blue, it is a head-on or initial opposite direction crash and had a very low TTC. So we expect a surprise event with an oncoming object. So if we look at this scenario, we see this is a very odd scenario. We can show it again, where basically this vehicle in front of us was involved in a crash, then went around the truck into the view of our sensors in our vehicle. So there was not a lot of time for the ADS to notice that there would be a potential conflict. And this is obviously an outlier case. We don't see this very often. And then let's say we look at the opposite direction, something with a very high TTC. So for this forward impact outlier, we expect a rear end scenario, just because that's generally what forward impact is, where the ADS would identify a conflict far before it actually happens. So in this scenario, there's a braking event. The host vehicle has a lot of time to brake before that car, before the crash occurs. And there's nothing in the way, so very high TTC. The reason it was included is because the subject reaction was later. So we can see that the driver didn't react until the very end. And because of this, they actually swerved a little bit onto that shoulder. And so after reviewing a lot of these events, we realized that the subject reaction was really important. And so we wanted to look at how drivers reacted in certain situations and how might ADS be able to respond to similar scenarios. So here's a visualization of some of those driver reactions. So out of the near crash cases in which we had sufficient radar, these are the number of the number of events in which the driver reacted this way. So there's no reaction at all, and then braked and steered, braked only, accelerated and steered only. The overlapped areas represent drivers' secondary evasive maneuvers. So for example, where the blue steered only overlaps with the braked and steered in orange, the drivers might have first steered only and then began to brake and steer, or vice versa. And so in the following clips, we'll look at some evasive maneuvers from unexpected events, which are areas in which ADS might have trouble performing that correct maneuver. So for example, in this case, the subject vehicle is going straight, and then another vehicle facing the wrong direction, but parked on that shoulder, then starts to come out into traffic. And so this is pretty unexpected and not a normal scenario. So these are some of the outliers that need to be included in scenario testing for ADS. Just because it is confusing what to do, and this driver just kind of swerved around, but that's a very complex situation when it comes to developing some ADS for that. In this one, we'll see a vehicle turning right into the oncoming lane of the subject vehicle, but they take a very wide right turn. So we'll see on the back there, this vehicle turns right, and they take such a wide turn that they go into the lane of that subject vehicle. And this confuses the driver, clearly, and so they swerve onto the shoulder to avoid a potential conflict. And so some of those very confusing scenarios would be complicated for ADS because the other drivers on the road are not doing what's expected of them. And then this one, this was a common scenario in which the conflict vehicle attempted to change lanes into the host vehicle lanes and cut them off. So we have the vehicle on the left cutting off the host vehicle in that center lane. And so in this scenario, the host or subject vehicle slows down and maneuvers to the right side of that lane to allow for that driver to cut in without a conflict. And these cut-in scenarios are very common, but it is a complex situation. This driver had to slow down and move over to the right just a little bit to avoid that conflict. And we don't know what would have happened if they just stayed in their lane, but it's kind of these complex scenarios we have to keep in mind for ADS. And then the ones we showed before were about kind of unexpected events. And this one is more on visual occlusion. So where the driver is very aware of their surroundings. We'll see they're driving along stop traffic, and then a vehicle pops out to attempt to turn into that lane with the driver. So just some scenarios in which there's a lot of context that sensors might miss. The sensors might not be able to see that vehicle, but the driver understands there's a line of parked cars, and so they have to be very careful in case something pops out. So that demonstrates good roadmanship or good drivership. So it's just some of these scenarios where ADS sensors might not sense another conflict, but there's a lot more context to the scenario that drivers have. So when it comes to visualizing these scenarios, the minimum required deceleration provides an insight into what would be required to avoid a collision using braking alone for ADS. So this graph shows the minimum required deceleration in meters per second squared on the bottom, and then the number of events on the y-axis. So basically, according to a study by AAA that looked at maximum deceleration values in automatic emergency braking scenarios, most AEB systems had an abrupt deceleration rate that was around 1G. And so this orange line demonstrates the 1G threshold. And we could simplify this then by stating that any events from this from ADS that require a minimum deceleration above the threshold of 1G to avoid a crash would not necessarily be feasible or be feasibly avoided by ADS. So in this case, 11.57% of the events from ADS required a minimum deceleration value above 1G. And so we could say that ADS couldn't avoid these events by braking alone. And we've kind of mentioned this in those videos and from here too, is something that is important in these scenarios that creates a near crash versus a crash is swerving. So having that lateral movement, which becomes a lot more complex in some scenario development. So in general, these safety critical events resulted in near crashes rather than crashes, just because there were 1% of the total events were crashes and the rest were near crashes. And they were mostly due to the successful swerving maneuvers by the driver. So this graph shows if we look at the longitudinal acceleration on the x-axis and the yaw rate as shown by the human driver. So these are the values that actually occurred from the human driver. If we then overlay it with those events, those 11.57% of events that would require over 1G of deceleration to avoid the crash, we see that most of the drivers, the actual drivers in this scenario, had a high deceleration, but also a relatively higher yaw. So generally those purple diamonds are higher in the yaw rate as well as deceleration. So anything inside the circle requires a low deceleration and low yaw rate. So anything outside of those might require more complex ADS development in how to avoid some of those crashes. So it was a little bit out of scope of this project to look into how the yaw rate affects crashes and near crashes. That's what my dissertation is looking into a little bit further. But it is very interesting to see how swerving affects near crash rates versus crash rates. So overall, did we answer the question, how safe is safe enough? The answer is that it's very complex. And also that safer than a human driver isn't even necessarily a good enough threshold, since we still take on a considerable amount of risk every time we get on our roadways. Humans themselves aren't even acceptably safe if we have this vision zero of zero roadway fatalities. However, this research also highlights areas where human drivers are pretty safe. So this is kind of contradicting the previous point, but specifically attentive, alert, sober drivers that are aware of their environment can perform complex evasive maneuvers that require more than just hard braking. And these events, this naturalistic data, these near crashes, can model what is acceptably safe or what is good roadmanship to help determine what some thresholds could be or what scenarios should be tested in ADS. So in conclusion, using a small set of naturalistic data has the potential to convey important information to wide-scale ADS deployment that just simulation or closed track testing cannot. So making sure to use naturalistic data, real-world data, to even inform some simulation scenarios or inform testing on closed test tracks that then can be implemented in the real world to actually use real-world events to use it for those testings to then see how it will react in the real world. And human drivers are generally good at performing evasive maneuvers that require braking and steering. And that requires a complex set of decisions for ADS. Braking itself can be complex. And so adding that steering maneuver and making sure that the ADS is aware of their environment and what steering is required makes it a much more complex area to work into. And ADS may not perform as expected in high-speed turns, blind turns and hills. And we didn't cover those specifically, but The last two, those lane change events with other vehicles and scenarios with significant occlusion we saw in some of those videos. But anywhere where the sensors don't have enough time to get a full picture of the environment is very important to look into. And in those cases, it would be great to have some more information. This is kind of out of the scope, but more information from the infrastructure, other vehicles, some information sharing to allow ADS to have more, a better picture of their environment. And then near crash and crash relevant events are absolutely crucial to understanding the complex driving context. There will always be more unknowns, but using kind of the near crash and crash relevant to define safety is very important. Fatalities and crashes are not the only things that make up what safety is. And so being able to look at near crash and crash relevant examples is very important in defining what safety is. And with that, I'd like to thank my safety team on this project. So Zach Dorzaf, Liz White, Andy Peterson, and John Hankey, and Laurel Glenn for all of your help, and the subject matter expert, Kevin Kiefauver, for all of your help in this project and in safety and at BTTI in general. But with that, I will take some questions. Thank you.
Thank you very much. We do already have some questions coming in. So the first one, can ADS currently perform swerving to avoid crashes?
Yeah, so at the moment, at least, we have ADAS features like automatic emergency braking are safety features. And then ADS right now is viewed as a convenience feature. So in general, it's more convenience for the driver and to avoid some of those risky scenarios. And so it is important to note that sometimes the ADS, although it does everything to avoid scenarios like that, like we saw, there are other actors on the road, right? And so there will be safety critical events. So right now, ADS, yes, does have they have longitudinal and lateral control, but it is viewed as a convenience feature, not necessarily safety yet. So this is really important just in the development of how to measure the safety of ADS and when they're put in some weird scenarios.
All right. We also have a question from Luke, who will go ahead and ask themselves. You may go ahead.
Hi, Eileen. This is Luke Grexinger. Could you explain again in your sample how the single vehicle roadside departure crashes were included?
Yes. Let me pull it up. Actually, I have another slide for that. So these were included as kind of the my extra ones. Okay. Kind of a catch-all for the other ones. So the roadside departure, it was not included in the like TTC events. I should have mentioned that before, but yeah, so those resulted more in actual crashes, mostly from traction control. So if it was a traction control problem, then it was removed. If it was due to another vehicle or object, that was included in the scenario selection.
Gotcha. Okay.
All right. We have a question from Rhonda. How representative is the data set that you use for your analysis?
So this data comes from a few naturalistic data sets that were conducted at BTTI. The largest is the SHARP2 naturalistic data study. And there's a lot of information online about it, but there were 6 collection sites, I believe, across the US and represented a lot of different drivers in there. So I don't have the numbers right now, but that would be important to look into. But it's, yeah, the SHARP2 naturalistic driving study at VTTI, it's very large. We have over 1 million miles of data on these crashes. Sorry, I don't think that really answered your question, but I can give you that information if needed.
There's actually a follow-up to that question, which is what ADS system capabilities were available in historical naturalistic data set?
Right, so in this data set, none of the vehicles were ADS equipped. So these are pretty much levels 0 and 1, but in these events chosen, there were no ADAS or ADS features available. And so the way that we calculated how an ADS would react, that's when the conflict was predicted. So that's when the radar would have predicted a potential conflict. And it is a simplified version. Since we don't have the actual ADS data, we don't know. It depends on the system, right? It depends on the sensors and the algorithm to predict when a conflict would be predicted. But that was a time point available in the data set. So we used regular human-driven data and then used a different time point to determine when ADS might be activated of a potential conflict. Hope that answers.
There's another question about the database. So is there a database of ADS crashes level 3 and 4 at all at VTTI that you are aware of?
Not that I'm aware of. The ADS availability of vehicles that are actually on the road are pretty limited. In terms of ADS vehicles at VTTI, I know we're developing some, or there's some data collection of them at this moment, but I didn't have access to that data for this project.
Okay, we're getting quite a few questions, and I encourage you, if you do want to ask them yourself, since you might have follow-up questions, go ahead and raise your hand and I will unmute your line for you. I'm going to read a statement here from an attendee. It says, I believe the question is here that would get us to the safe enough what would get us to the safe enough stage? Are we driving in the opposite direction of safe enough? Bigger cars, wider roads, higher speeds, more distractions in the cars, less drivers licensing restrictions, etc. Is the answer really ADS or CAV? Or should we start to drive in the right direction towards safe enough? Then we can turn to look at how these technologies could help.
Yes, big question. See, I have it here too. How do we get to the safe enough stage? That is a big question. So I think a part of it, you mentioned CAV, so connected automated vehicles. That's part of a project that I worked on before, and kind of where my dissertation is heading is where if we have all these ADS developed internally and all of the vehicles house the sensors, there's a lot of the driving context that is unknown. It's only what the sensors can see. So if we allow some connected abilities between either those vehicles and the infrastructure or other vehicles, that expands the driving environment that is known by the ADS, and so they can react appropriately. So similar to those visual occlusion cases, it gives the vehicle more context where the sensors can't really see. And sorry, there's a lot to that question. Are we driving in the opposite direction of safe enough? That is an interesting question. I think people in the industry, at least, we were expecting automated vehicles to come on the scene much quicker than we are. And now we've kind of pumped the brakes to make sure that they are safe enough. So I don't think we're driving in the opposite direction of safe enough, but I think there's a lot more context we need to understand. And that was the hopes of this project, is shedding light on some of those near crash cases, especially, and some of the weird scenarios that happen on our roads that developers might not think of. So whether that's giving some kinematic thresholds of how good drivers might react, or just creating more scenarios to test, that's kind of the hope of this project, is shedding light on some more scenarios and what needs to be focused on as well.
All right, talking about those scenarios, did your research also highlight unpredictable pedestrians and animals?
Yes, those were a big part of it. I know when it comes to pedestrian and animals, a lot of ADS manufacturers or developers are coming up with totally different algorithms just because the way they're identified is different and the way they move is a little bit more unexpected. Especially with pedestrians and animals, they have 360 degrees of freedom, right? They can't just go forward and back. They can go in any direction at any time. So that was included here, mostly in the visual occlusion cases where people were popping out of a long line of cars, or just unexpected when pedestrians on the sidewalk kind of just jumped out into traffic without indicating that they would do so. So that was included. It was more that was included in like the TTC required deceleration if that person if that conflict was predicted, but then also mostly in the video review. Another thing I didn't mention were items in the road. So a lot of times there were just objects in the road. And that is also something that might be complex for ADS to view because it's hard to identify what that object is, and that might complicate some sensors that they have right now. All right.
Okay, you still have more questions. Irma's gonna continue to ask. Sorry.
No worries.
We have one question from Anonymous. Did your research also highlight unpredictable pedestrians and animals?
Well, that was the one we just did, actually.
Oh, I'm so sorry.
That's okay. It's the next one.
How did you measure ADS TTC, and which ADS or model of ADS was used?
So let's see if I can pull this here. See, I can't change here. So TTC we used the radar on the vehicle. So I mentioned before the vehicles themselves were not ADS or ADS equipped, or those features were not on at the time of the event. And so the TTC was the range rate divided by the range. So that relative velocity of the subject vehicle and that conflict vehicle divided by the distance. And so that gives you that time, or the opposite. But anyway, so that was for the human drivers. And then, so that was at that T3 time point. Let me see if I can pull that up. Oh, here we go. Sorry, at T2. So the subject reaction. So when that driver reacted. And then the T1 was when the ADS would have began an evasive maneuver. So we calculated the same TTC, but there's a different, obviously the vehicles are either further apart or it's going slower or faster. So the TTC calculation is the same, it's just at different time points in that scenario. Hope that helped.
Thank you. Next question is from Claire Fisher. Do you think there is a sufficient source of naturalistic driving data for future researchers to leverage for ADS development, or would it be beneficial to continue gathering naturalistic data to further this field of research?
I mean, more data is generally better, not always, but I think collecting more data, especially now when vehicles on the road have more and more are equipped with ADAS features. So not just safety features like automatic emergency braking, but more of those convenience features like automated cruise control or lane keep assist. So there's more vehicles on the road kind of that are being that have the vehicle in charge rather than the driver. And so the data, I'm assuming, is a lot different. And so I think collecting more naturalistic data as more automation is included in the roads is especially important, especially as ADS starts to be developed like in some rideshare programs and other developers that are actually putting ADS on the road, I think collecting more naturalistic data is still very important.
Thank you. Our next question is, what ADS level are most cars currently equipped with, and what level are the prototype test cars at right now?
Yeah, so publicly available vehicles for purchase right now are level 2. So that's kind of the new advanced vehicles that give you the longitudinal and lateral control. So like I mentioned, adaptive cruise control and lane keep assist. Those would all be level 2. And the ADS vehicles, level 3, 4, 5. There are some level 3 and level 4 on the road. Those are they're not publicly available to be purchased to the public, but they are, there's some pilot testing on the road, like Waymo has some. And so there are some ADS on the road, and there are some like last mile vehicles on the road that might bring people from parking lots to their building that are automated and would be considered level 3 or level 4.
Thank you.
Yeah.
The next question is once again by Claire Fisher. Did your research include any analysis of the use of ADS in vehicles, such as public transportation buses or delivery trucks?
That's a great question. This data set did not have any analysis of public transportation buses or delivery trucks. There are some separate projects that are working on ADS and ADAS features in some of the buses or trucks. And actually, that's how I'm now a researcher in the heavy truck and bus division at VTTI. So that's kind of what I'm looking at more in my work. And so it's been interesting to see how different it is in some of the larger vehicles as compared to the light vehicles in this study.
You.
Mhm.
And if anybody has any further questions at this time, if you will raise your hand, I would be happy to unmute you so you can directly address the questions to Eileen herself.
All right, thank you, everyone.
All right. So what I'm going to do right now, thank you everybody for all of the great questions. I'm going to go into the chat right now, so everybody should hopefully be able to see this. If you do not, let me know. She has already finished her paper, so I'm going to send a link right now to that paper so everyone can go ahead and get all that data, because now it's all the interest, and you can get more information on everything that she actually did. And let's see, we also have, if you do have any more questions, you can continue typing. I just want to thank everybody right now for joining this webinar. This webinar will be uploaded on YouTube. We are recording, so once that is complete, everybody who is registered will be getting an email from safety notifying that it is up. I will send you a link with that, in fact, an entire citation along with Eileen's presentation. So you will get all of that available to you by email. As soon as it's up, it should be up within a week. We also have further 2 more webinars that we have coming up, and we have 1 more actually listed. I'm going to drop down another link for you right there in the chat so that you can see the upcoming webinar. The next one is on a conceptual model of the ADAS ecosystem and gaps in the literature and research needs. Is going to be presented by researchers at the Texas A&M Transportation Institute, and that is scheduled for February 15th at 2:30 Eastern Standard Time. You can go ahead and register for it now. I'm going to also send you that registration link in the chat So you can do so if you wish. Aaron, were there any other questions? Oh, someone says the link
Yes.
is a bad gateway. That's not good. It just worked for me. So I just put it up there. So I was trying to hurry up.
We
But
have
I
one
will.
question, I think. As
Go
a
ahead.
driver from a northern state, I've observed how drivers are better at winter driving at the end of winter than they are at the beginning. Has anyone studied the impact on how access to ADS will affect the ability of drivers to take over when ADS is not an option?
That's a very interesting question. Yeah, and I grew up in Wisconsin and we had lots of snow, so I can relate to that. I'm not aware of how ADS has affected the ability of drivers to take over when ADS is not an option. Yeah, so there is some research in takeover requests. And especially on driver monitoring. A previous project I worked on was looking at driver monitoring systems and how to predict the level of attentiveness for drivers. And so there's also a difference in making sure that drivers are aware of the driving environment, but then also able to take over if ADS fails. And so there's both the distraction component, but then the takeover readiness. And so it is a very complex topic. And I'm not sure how the addition of ADS availability in our roadways might change how drivers drive. It's more of a human factors problem that I think is very interesting. But I think I've heard of some projects that are trying to tackle this, but I'm not aware of anything specifically. Hope that answers.
I believe we have another question. It's from an anonymous guest. ADS may likely have LiDAR capabilities. How might the introduction of LiDAR change these results?
I think that's also a very important question. So this, let's see if I can actually change this slide too. Yeah, so this project, we had radar available for the vehicle. And LiDAR would obviously change the available data that we have. Also, this project assumes that the radar is correct as long as it's there, and we validated it through watching the video. But having the different sensors definitely makes a big difference on the capabilities of ADS. So just having different sensors and then the sensor fusion algorithms to make sure that all of them are working correctly, and then also the algorithms that are used to determine the maneuvers of the vehicle. So there's a lot of moving parts. And so obviously using LiDAR would change it significantly. The hope is that it would improve it. Just generally LiDAR has a better awareness of the environment and in certain conditions. So it would change the data is my short answer.
There was a question about making the questions public once they're answered, and I am moving that into the column. So hopefully you guys are seeing that now, and hopefully that link is now also working for everybody. If not, just go ahead and shoot a message. Aaron, it looks like a few more have popped up.
Yes. Would ADS ever engage a horn as a safety measure?
Ooh, that is a good question. I'm actually, I haven't heard of what the ADS might do to alert other people and other vehicles on the road. That is a great question. I know some projects at VTTI specifically have been looking at how to notify pedestrians on the road that an ADS is approaching them by using like light bars to show if the vehicle is slowing down or speeding up. So it would be really interesting to see maybe what other what other scenarios there are that ADS can employ to notify other drivers and other people on the road. But yeah, I'm not aware of any.
Thank you. And I think that is what we have so far from questions. We don't seem to have any new ones.
All right, well, we will go ahead and thank you again for a lot of questions, a lot of awesome questions and conversation. And again, Eileen, thank you so much. We have a couple more minutes, so she is going to stick around in case you have more questions. And again, if you want to talk with her yourself, you can raise your hand and we will unmute your line.
Yeah, thank you all for listening and for your questions. And yeah, like Laura said, I'll stick around a bit.
All right, thank you.
Thanks.
For those of you that say that the only one is working is a registration link, I am sorry, I'm not sure what's happening. It's working on my end, but that does not do you any good. And we'll keep working at it. And also, I will send all of this out still, everybody who's registered. So if you are in this right now, you will get the actual link to the project then too, if I cannot figure out why this site isn't working. And from there, you can also download it, and I can send you a direct link as well to everybody when I send out the actual webinar and the slides. So rest assured you will get it. I can't figure it out right now. All right, well, we're gonna go ahead and close off. Once again, thank you to everybody. Bye-bye.
Thank you all.